করে দিয়েছি।
হ্যাঁ স্যার হয়ে গেছে, আপনি স্টার্ট করে দিতে পারেন এবার।
Okay. So I guess at least 100 of you have already joined. I don't know how many of you are left outside the room. What is the
Sir,
total strength? 120?
123 sir.
123 sir.
Okay, so maybe 20 odd people are still out of the room. Okay, I guess they can go through the video recording. Since this is not a formal class, actually you can call it an extension of your signals and systems class, right? These portions were supposed to be covered in signals and systems, but due to this pandemic situation, I couldn't cover it. And in your assessment also, this was excluded. But some of you have gone through this experiment, that analog simulation, in your second year, second semester, right? How many of you have gone through this experiment, analog simulation of second order systems? Anybody? Shubhankar?
হ্যাঁ স্যার লাস্ট দিনে করেছিলাম এটা।
তোমাদের I think 2 or 3 batches at least have done the experiment, right?
4 to 5 batch.
4 to 5 batches. Okay. So almost half the strength. And what about the other section? Ankit, what about your section?
We have also done.
কত করেছে তোমরা তো?
হ্যাঁ স্যার।
তোমাদের কি আমি করেছিলাম না অন্য
স্যার
স্যার?
আঙ্কিত শুভঙ্কর
আপনি করেছিলেন।
আমি করেছিলাম।
হ্যাঁ।
হ্যাঁ, তো ভালো হলো, আমার তো খাটনি কত কমে গেল। Those who have already done the experiment can explain to the others. I will just sit back and enjoy. কি বলো?
হ্যাঁ স্যার করে দিতে পারেন।
না this is just
আমি করিনি তাই না বললাম।
Okay, so that is the point. No, there is a very common story behind that. Once, if I am not wrong, it was related to Mullah Nasiruddin. He was asked to give a lecture, so he went to the class and asked the student, any idea regarding the point that I'm going to discuss today? So they said, no sir, we have no idea, you are the teacher, you should be teaching. So he said angrily, no, I'll not discuss anything with the so dull students. They have no idea about what they're going to learn, so I'll not take your class. So he left. So the students thought, okay, sir is right, so we should be prepared. The next day they requested him to again say, please come, we'll be prepared. So again he asked the same question, do you know what I'm going to discuss today? Everybody said, yes sir, we know. Then he said, okay, if you know everything, then why should I waste my time? So I'll not take the class today also. See, this way 2 days gone. So third day, the teacher again came, Mullah Nasiruddin. Students were they thought they were very clever. Half of them said, yes, we know, and half of them said, no, we don't know anything, sir. So he was very clever, even cleverer. He said, okay, those who know, just explain it to the other half. So think of something like that. Some of you know the experiment, so you can better describe the experiment to the other. That can be the possible solution, but this is not a class for obtaining such easy solutions. So I'll be explaining the things. Before that, I think it should have been covered in the class, so I'll just share some ideas on that. Okay. So this is, I'll provide you with these notes, okay? Analog simulation. Now, this analog simulation is basically simulating an mathematical equation via electrical circuits. If you remember, in our signals and systems class, what we have covered in the lectures that you've got, first was modeling of dynamic systems, and these dynamic systems were characterized by differential equations or integral differential equations. So to obtain the response of the systems, we need to solve these integral differential equations. So we have discussed about different techniques, Laplace transform techniques, and other obvious techniques that they are to solve these differential equations. But these are purely mathematical techniques. And in some situations, we need to have a physical interpretation of the response of these systems. For that, what you can do, we can simulate the systems. And this analog means it will be simulated in an analog environment, that is comprising of analog devices like op amps, atmos resistance, and capacitors. That will be the devices or the instruments or equipments that you will be having. Okay, so if you remember, there was also a topic that I covered. There was analogous systems, right? That is a class of systems. They may be different physically, but they share a common differential equation that describes their dynamic behavior. It may be a huge mechanical system and a small RLC system, RLC series circuit. They're having identical differential equation. So the dynamics will be identical. So what you can say, the electrical RLC network will be analogous in behavior to the mechanical system, right? The advantage that we found out was that it is very difficult to carry out different experiments with complicated or large apparatus. So if you can obtain a idealized model of the apparatus, then we can very easily simulate that in an electrical environment using RLC components, and then we can go for analog simulation. Now, this simulation can be done based on RLC components. That's okay. It's very easy to find out the required value of RLC. But problem is that in that case, for different situations, you need to change your R, L, or C values. So in some situations, that may not be very much recommended. So what you can do, we can go for another way of solving the differential equation using op amps. Now, these op amps will be used in different common structures. All of you can see the screen?
Yes, sir.
Okay.
Yes, sir.
So to solve the differential equation, we need a few common blocks. One will be like this, a summer or subtractor block. Okay, this is a summer or subtractor block that can be easily fabricated using an op amp. Okay. There will be a multiplication by a constant block. This multiplication blocks will be required. Just suppose we have a differential equation x double dot plus ax dot, sorry, plus bx equal to c, suppose. So this a, b, and c are the constant or the coefficients of this differential equation, and this x is a variable of interest. So we need to find out the value of x by solving this differential equation. So what we will need? We will need a summer like this, summer or subtractor like this. We will need a gain or multiplication by constant that will interpret this a, b, and c values. And then in some situations, we may need a sign inversion. And most importantly, last but not the least, we will require an integrator, right? Because we need to integrate x double dot twice to get x dot and then x. So given a differential equation of say order 2, we need to integrate it twice to obtain the value of x. It's a very common mathematics. Now, how this thing can be carried out in an environment, laboratory environment, let us discuss this. So for that, let us start with a very basic example. Say we have a differential equation. This is a differential equation. We need to solve this differential equation, right? So what you can
হ্যালো আপনার ভয়েসটা কেটে গেছে
তোমরা কি আছো? আমি মানে মিটিং থেকে বেরিয়ে গেছিলাম।
আছি স্যার।
স্যার
হ্যাঁ স্যার।
আর এখনো আছি।
আচ্ছা, স্ক্রিন কি শেয়ার হচ্ছে তো? স্ক্রিন দেখতে পাচ্ছ?
না
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 স্যার
স্যার।
নো স্যার।
এবার
হ্যাঁ স্যার, মানে ব্ল্যাক আছে এখন। হ্যাঁ এখন ঠিক,
এবার
ঠিক আছে স্যার।
ঠিক
Okay.
আছে।
আচ্ছা, আমি বেরিয়ে গেছিলাম, আমি জানি না কতক্ষণ বাইরে ছিলাম। I will just start again. So to solve this differential equation, this can be easily solved by this integration, a single integration. So this integrator is over here, right? Now we know this yt is nothing but dy dt. So if we have this dy dt signal, then this is nothing but your yt signal. So if this is dy dt, you integrate dy dt, what you get? Yt. Look carefully. If this signal is dy dt, upon integration, what you'll get? We'll get yt. But as per given relation, this dy dt is nothing but your yt. So what you can do, you can simply connect this output to input, and whatever output you will get from this integrator will be the actual value of yt. So this is a very important aspect. In this analog simulation, we need not worry about instantaneous value of dy dt or y. What we need to ensure is that the correct mathematical formulation is followed while connecting the components. See, we need to integrate dy dt to get y, first of all. Then what should be the value of dy dt? Given the equation, we know dy dt is nothing but y. So you can simply feed back y from the output and put it to the input of the integrator. This will give you the actual output. And again, we have to add simply this initial condition. These provisions are there in the integrator. So this is how you can solve a simple differential equation. Since it is a first order differential equation, a single integration will suffice. Now, everybody understood this?
Yes, sir.
Yes.
কোনো confusion নেই? Okay, very fine. Let us go one level up. Hi, Ankit. Okay, let us consider a second order differential equation, right? So what we have here is a second order differential equation with two initial conditions. We need to solve this differential equation to get yt. So to make things easier, let us define two variables. First variable x1, which is equal to y, and x2, which is nothing but y dot or x1 dot. So these are two variables that we have declared. So first set of equation will be x1 dot equal to x2. Very easy from here only. And initial condition x1 0, that is nothing but y0 equal to 1. And the second set of equation will be x2 dot. Now what is x2 dot? x2 dot is nothing but y double dot. So from this you get y double dot equal to minus y dot minus y. Minus y means minus x1, and minus y dot means minus x2. So this is the second set of equation with initial condition like this. So these are the two equations that we obtain from given differential equation. Now we need to simulate the equation. So how can it be done? See this equation, x2 dot. What is the value of x2 dot? This point. x2 dot is nothing but minus x1 minus x2. So if you integrate x2 dot, what you will get? x2. Now again, x2 is nothing but x1 dot. So this signal is again x1 dot, and this signal is obviously x2 dot. So if we integrate x1 dot, what you will get? You will get x1, and x2 dot, which is here, is nothing but minus x1 minus x1. So this minus x1 and minus x2. So you need to just connect these two outputs over here to a summer. So what you get at the output is the actual value of x1 as a solution of this differential equation. X1 means nothing but your y, the desired value. Okay, I'll make it a bit clear. So basically, x2 double dot is equal to minus x1 minus x2, right? And x1 dot is equal to x2. So this is x1 dot, integrating you get x1. And this is x2 dot, integrating you get x2. So you have two information, x2 and x1, that you're getting by a signal x2 dot. So what information do you require? x2 dot. So this can be computed using x1 and x2. Basically, they are interleaved. x1 and x2 both are interleaved. Other way around, if you know x1 and x2, you can obviously get x2 dot. Okay, so in this case, the relationship is very important, not the instantaneous values. Since these all will be an analog system and they will continuously be updating themselves, right? This integration will be analog integration, continuously updating. This is again continuously updating. So whatever value you'll be getting from these two signals will be fed back to update the value of x2 dot. Correspondingly, this value and this value will change. So you'll get a continuous propagation of the signals x2 and x1. Okay, that state variable analysis hasn't been taught in a control system class. State variable. I have given you some example or some initial impression on state variable, if I can remember, that RLC series circuit, right? In that case, there was second order differential equation. There are two state variables. Here also you can consider this to be two state variables, x1 and x2. And you can simply get these two state variables from this x2 dot signal. So this is how this analog simulation works. Now, the important thing is that we've been discussing about this summer integrator. How does this blocks actually look like? I think you have quite a good knowledge of analog circuits, that op-amp circuits, right? Operational amplifier. I should not waste time on this, okay? The standard operational amplifier, I'll just skip through. This is a summer, an inverter, right? The very common things. Okay, the only thing that is important is that gain, constant gain terms. These are obtained by a potential divider, or you can say pot, where we're giving input voltage, and this has effective value 0 to 1. That is this alpha value. It varies between 0 to 1. If it is over 1, that means at the output you are getting the entire voltage drop. That is this drop. But when it is 0, that means you are not getting any voltage at all. It is grounded. So by changing this location of this, you can change the value of alpha, but it will be within 0 and 1. Okay, not beyond 1. So any coefficient that is 0 to 1 can be easily fabricated using this system. The next question is, how can you ensure that all the coefficients in a differential equation will be between 0 to 1? Now, to take care of that, in our operational amplifiers, just a second. This is the experimental setup that we have. Say these are simple summer blocks, okay? And we have 5 input ports, 1, 2, 3, 4, 5. Among them, first 3 has a gain of 1. So whatever signal you're getting over here will be simply multiplied by 1 or simply passed through. But these two last two, they have a gain or multiplier of 10. That is, whatever value you give here will be multiplied by 10. So as if the coefficient, whatever coefficient you set, will be multiplied by 10 over here. So to set a value of say 12, what you can do? You can simply, okay, say 1.2, not 12, say 1.2. What you can do? You can set the port at 0.12, the potential divider, and then use this input. So it will be 0.12 into 10, 1.2, right? So what about 12? If it is 12, then you have to use another such summer, so that it will be inputted over here first, then following the output, it will come over to here. So 10.12 into 10, at this point it will be 1.2, and then again into 10, at this point it will become 12. So by this way, by cascading such op-amps, you can obtain any value, but the port will give you only values between 0 to 1, okay, with 0 and 1 both included. So I've been talking about ports. These are the basically the ports that you will be setting in an experiment, okay, and these ports will indicate your coefficient values. See, one thing, in these ports there is no marking, there is no graduation, okay. So how you can set the port? There is a mechanism for that. So it can only be at 0 or at 1 or in between, but not more than 1. So we have to use this amplifiers, and these are all inverting amplifiers, okay. Some are subtractor, whatever they are, or simply inverter, they're all inverter. So you have to always keep in mind. So I'll discuss about the lab in the next class. This is just for your sake of understanding. So these have been the port. Now the integrator, I think you all know the basic integrator circuit that comprises of a capacitor and resistance. Since there are provision for multiple inputs, so this will be something like this. Okay, I'll not indulge into this topic anymore. So just keep past this. Okay, the symbol, whenever you are drawing an analog simulation, the integrators will be symbolized like this. This portion indicate that it's an integrator. Okay, and this is your initial condition. Every integration requires an initial condition that can be incorporated via this port. So in case of normal summer, we normally use this symbol, but for integrator, we need to use this symbol. Sorry. With this being the initial condition. Okay, this you should keep in mind. This is a summer subtractor inverter, but this is an integrator. So now, with this brief introduction to all the components that we'll be using, I will discuss this in the next class after showing you the actual figures of the results. Now, a systematic procedure for developing analog simulation. Let us consider an example, right? So what we have here is a differential equation, right? With say initial conditions. These are two initial conditions. So far what we have discussed, that to obtain the value of xt, what you need is the only information on x double dot t. Because you can always integrate this twice to get xt. Okay, but since this is a second order equation, we also need the information on dx dt, because if you write down the equation in a standard form, what you'll get, x double dot will be equal to 4 minus 0.5 x dot minus x. So this will be the differential equation. So this x double dot will be dependent on a function of a constant input of minus 0.5 x dot. That is, you integrate it once to get x dot, then feed it back to the input, and then you integrate this again to obtain x and then feed it back. So this is a simple connection with, at each of the integrators you need to incorporate the respective initial conditions. So this is how you should proceed with this. Shall I ask you to draw a corresponding analog diagram, how it would look like? Can anyone draw that? This diagram for this equation? Just a second. Okay, rather leave it. I'll show you. In the next day, I'll give you some assignment, and based on that, then I'll ask you to draw something. I'll give you some problem. Okay, for the time being, let us proceed. So we need to obtain analog simulation for this. Let's see. So this is the first step. What you have to do, you have to write down the equation in this standard form. Okay, with the idea that once you have the information on x double dot, you can integrate it once to get x dot. Most important thing to note here, these integrators are all inverting integrators. So x double dot will not give you x dot, it will give you minus x dot, right? This should always be kept in mind. And then integrating it again, we'll get x. So this is the standard forward path. Now, the next term will be to obtain this x double dot as a combination of this x dot and x. How that can be obtained? See, we have already written the equation. So this x double dot, keep in mind, this is minus 1, this is inverting, should be equal to 4, since it's plus 4, we need to incorporate an input of minus 4. Understood? So at the output of this summer, it will be plus 4. Then what we have? Then we have minus x. So to get minus x, we need to incorporate simply x. Okay. Then what we have? Finally, we have minus 0.5 x dot. So we have to give 0.5 x dot to get minus 0.5 x dot. So at the end of all this summation with proper inversion, see, you're getting x double dot, that is nothing but this equation. Just check whether you're getting the correct equation or not. Minus 4, minus 1, plus 4, check. Plus x, minus 1, minus x, check. 0.5 x dot, minus 1, minus 0.5 x dot, check. So this will result in x double dot signal with proper signs, and that conforms to this equation that we want to solve. This is actually the equation that you want to solve. So once you get x double dot, simply you can integrate it twice to get x. This is a simple procedure. Now let us put this theory to practice. In actual scenario, we need to obtain the connection. See, this will be the connection. See, to obtain this x double dot, what we are doing, we have a minus 10 volt source with a 0.4 port setting, this port. So what will be this value? Minus 4 volt, that is constant part is taken care of. Okay, assuming that this is x double dot and we have put an integrator over here. So this will be minus x dot, right? But our equation demands that this x double dot is nothing but minus, it was plus minus 0.5 x dot. So what we have to incorporate here at this point is plus 0.5 x dot. So this is already minus x dot into 0.5. So minus 0.5 x dot. So it has to be multiplied by this inverter. So minus, this will be plus. So at the output of this inverter, it will be minus. So it will conform to the equation. I'll just put the equation over here. Four, it's minus. So out of this inverter, it will be plus 4 minus x dot c minus x dot minus 1 plus x dot into 0.5 plus 0.5 x dot. After going through this inverter, it will be minus 0.5 x dot, and last term that is remaining minus x. So after integrating this minus x dot with an inverting sign, we'll get x. So to get minus x, this input should be x, so that x double dot becomes this minus x. So this is the actual connection. If you look closely, so this x double dot is, what is it showing? 4 minus 0.5 x dot minus x. So once you have the information regarding x double dot, simply integrate once to get minus x dot. Important thing is this initial condition. This initial condition is again fed through an inverting channel. So to get minus x dot, if you get minus x dot, the initial condition should be that of minus x dot 0, right? Since it is again fed through an inverting channel, you need to put a minus sign over here, so that the actual initial condition is reflected over here. Reflected over here. Again, see, this is xt, so initial condition should be x0. But since there's an inversion involved here, you need to put a minus. Yes? Any confusion? Say initial condition is, in this initial condition for x0 is 1. So you have to put minus 1 signal here, or minus 1 volt over here, right? And your x dot, sorry, so this is 2. So what should be the value you put in? You should be putting over minus 2, minus of minus 2. So you should put a 2 volt signal over here, right? That is the thing that you should keep in mind. This will dictate, let me clear everything out so that you can understand. This will dictate what should be the initial value. But since there's an inversion involved over here, you should put an inverted value over here, right? So this is how things would look like. Now, this is not all. See, in this connection, there are 1, 2, 3, 4 in fact. See, this 1, 2, 3, this connection. This is redundant. Why? Already you have seen that this integrator has 5 input ports, right? So we are using only 1. Rather, we are using a summer, inverting summer. So this will complicate the situation. There will be more number of connections, more possibilities of loose contact, more complicated circuit, more number of wires involved. So what you can do, we can simply eliminate this part and incorporate this 1, 2, 3 signals directly to this part, to this integrator. Since this integrator has this provision for 5 inputs, right? So what we will do, we'll simply connect. Okay, let me just clean this thing up. Our relation, just look at this very carefully. See, for this path, it was passing through an inverter. So if we remove this inverter, so this inversion should come over here and make this one positive. Now this becomes plus 10 volt. Understood? Because we have withdrawn an inverter. Next step. What about this signal? This X was going through an inverter, but we have withdrawn this inverter. So what we should do? We should add an inverter so that the signal remains same when coming to this integrator. Because here an important function is the integration should be done on a proper equation, right? Or a proper relation. The relation should be maintained at the integrator end. To ensure that, we should add an inverter because this inverter is omitted. So this inverter has to be added over here. And third, say this line, it had one inverter, another inverter, two inverters. So if you omit one inverter, you can simply omit the other one also, right? So plus minus. So this will be simply coming through this. What it does, it makes the circuit much simpler. I think you can appreciate that, right? An entire block of op-amp and its connections are eliminated. This entire block is eliminated. Rather, we are using this integrator to its full capacity. Okay, and there's only a slight shift of this inverter from this path to this path. That doesn't count here. So this omission will make the circuit more concise or precise, right? So we'll be using this for our analog simulation study, right? So given any differential equation, if you're asked to solve the differential equation and show the actual response of this variable x with respect to any input, then this will be the circuit of interest. So this is how you obtain the analog simulation of a differential equation, and from that you obtain the corresponding output or the nature of the output directly. You need not bother about your intermediate variables or anything, right? So this will give you direct solution to the differential equation without any fuss. You just need to make sure that all the relations are maintained properly throughout the circuit. Okay, so this thing we'll be carrying out in laboratory experiment. Okay, there are a few analogies that I think I should talk about so that you can relate this to your standard class. Okay, what are those analogies? See, suppose in your those who have done this experiment in your regular classes might be able to understand this thing. This was the equation that was given to you. Pardon me for my poor handwriting. Is 1.9x equal to 0.95 u. That was the equation that were given, and you were asked to solve for x from this equation. Now, if you take Laplace transform of this equation with u as your input and x as your output, so your final transfer function, that is your xs by us will be right, and this is a very standard second order equation, right, and that is equivalent to a very standard equation. So what is the value of k? It is 0.5. So if you just have a look at the response, now what is the value of u is say a 10 volt step. So if we draw that, so this is your ut, sorry, I made a mistake, it should not come beyond this. ZUT is your time axis, and this value is 10. Now, since this is a second order system, and your response will depend upon the value of zeta. So, given a particular value of zeta, the steady state value will be here, is at 5 volt, and depending upon the value of zeta, you'll obtain different responses like this. It may be like this is underdamped, critically damped, or it may be completely undamped. Okay, depending upon the value of zeta that you choose, you can obtain different responses. The thing is that this responses, that is your xt response, you can observe directly at the output of this op-amp circuit directly. There is no need to go for any other thing. It will be shown if you connect an meter at the output of that, right? I'll just show you the experimental setup so that you can get an idea. In experimental setup, this analog meter is there. If you put the input over here, this needle will move like this, indicating the oscillations in the values. From that, you can have an idea about how the output is actually changing with respect to time. Okay. Now, coming back to this. So, this is basically a second order system, and the response that you are getting over is a step response. So, by solving this, assuming this ut to be a step function, now how can you simulate a step function? Just switch on the power supply directly. This power supply, if you switch on it instantaneously, that will simulate a step signal. So for given a step signal, the response will be something like this. So for ut being a step signal, solving this differential equation is equivalent to obtaining the step response of this transfer function, right? And we have already seen, I'll just put it like this, that this transfer function can be represented in analog simulation like this. How you can interpret that? First of all, let us draw two integrators, and hypothetically this value should be x double dot, this value should be minus x dot, and this value should be X. Okay. So can anyone dictate how should these inputs or outputs be connected? Say this is your UT. Say we have a 10 volt source over here. So there's a 0.95 into UT. So this should be connected to port 0.95 to this one. Is there anything that you need? An inverter or something? Anybody?
No, sir. Here I don't think we need, because 2 times it will get inverted, so it will be okay.
So I can connect it directly. Right, exactly. Again, this should be connected directly. No point in. Okay, so first one is fine. Next, you have the signal minus X dot. That is to be fed back over here with a gain 0.8.
So here a negative should be given, sir.
Sure? Think about it. Think about it. Any other opinion? Just chalk it out. You have your equation, right? You have your equation over here. So X double dot should be minus
Not
0.8.
given because negative output
Directly
is
to
coming.
integrator.
So will it be required to have
Direct,
an
no, sir, directly.
Right. And the last one, sorry. Pardon me for my poor drawing. This electronic boards are very sensitive. So I cannot go for 1.9. So I have to go for 0.19. Inverter or no inverter?
Yes, sir, there is needed.
Okay. So what we can do, we can simply use an inverter with gain 10. See? So 1.9 we have achieved. Agreed?
Yes, sir.
So at the output of this, we'll get a response, 100 amp response, because what is the zeta value over here? If you calculate, your zeta value will come something like 0.29. So your response will be typically an under amp to 1, something like this. Okay. So now if you change this 0.8 value, obviously this zeta will change, keeping omega n fixed. So you'll get different sort of responses, but the steady state value will remain same. Right? So this is how this analog simulation has to be carried out. This all that we have discussed till now are based on your secondary experiment, right? This all has to be covered in your secondary experiment. Okay, I'll just briefly cover that experiment in the next day, and then concluding part of this lecture. Okay, now let us come to the actual experiment. That is your third year experiment that we should discuss now. Problem is that suppose in some case you have a system like but say zeta is equal to 0. So it will be undamped response. And say k equal to 1 for say. So if input is 10 volts, so your output will be maneuvering like this. Now, in analog simulation, since it is done based on op-amps, all the op-amps, have a bias. Say plus minus 12, plus minus 15. In our case, we'll restrict our op-amps to a value plus minus 10 volts. Because we know if we reach beyond this threshold, the output of the op-amps will get saturated and the linear behavior will be lost. So we should keep the values, the output of the op-amps within a permissible range of say plus minus 10 volts. In case, since this K is 1, and for undamped case, we're getting a value of 10 peak to peak. So this is a boundary condition, limiting case. In case this K becomes 2, then what would be the final steady state value? It becomes 20. So clearly, this will not be shown at the output because the op-amps will all saturate at say 12 or 15 volts. So you'll get a flat top response that will not the actual response of the system. Since all the systems are interconnected through these feedbacks, the entire response of the system will simply not be flat top, but it will be completely different and it will not be the same as you expect. So what we can do is a magnitude scaling. That is, we need to scale down the entire problem so that the range of variation is restricted within the range that is permissible. Okay. So let us consider an example. Say we have a mechanical system. This theta is an input. Okay. And these two K's are same. And we have these values. This is given in your actual problem sheet. Sorry. This should be K. This is K, not F. And your F is a variable with a nominal value, say 1.25 Newton meter second per radian. So given this system, the actual value or the amplitude scale value of theta max is 2 radian, theta dot max is 2 radian. So both the outputs, if we supply from a 10 volt source, will reach a value of 20 volts. So that is beyond the permissible range of this op-amp circuit. So what we need to do is to scale down this value so that this theta max, instead of being 2 radian, should come down to 1 radian, so that peak to peak value should remain within 0 to 10 volts, right? So this is how magnitude scaling should be. This is when the magnitude scaling will be required. So in your actual experiment, we will be doing some magnitude scaling. So I will just briefly explain the method corresponding to this problem. In your actual case, I'll give you some notes, okay, so that you can go through it. So in the next class, when we will be concluding this, you can simply relate what you're actually doing in the experiment and what should be done. So for that, suppose we have that experiment, equation theta dot plus k theta. This theta is the input. So what you can do, we can simply define another set of variables . This within the parentheses are called the computation variables. They are not actual variable, but they are a cofactor or the fraction of the actual variable. If we put this equation or variables into thing, so what you'll get ultimately a new set of equations. So what you'll get, the actual input to the system, which was initially say 10 volt step, will seem like a 5 volt step. So gains will remain same, but under damped condition or any other condition, peak value will only reach a value of 10 volt. Initially, it was reaching the maximum threshold value of 20 volts. Since it was very simple and very ideal condition that everything was just double, which is simply can divide the actual value by 2 to obtain the scale down value. But in actual scenario, I'll give you some problem sheet with some solved problems where this is not that simple. But for experimental purpose, we'll just go through this simplistic circuit where you define another variable and correspondingly your circuit connections will be modified. Okay, and you have to just keep in mind that these modifications are to be incorporated while selecting these gains, this J, F, and K. These gains will all get changed, right? Obviously, this J will be, sorry, J by 2, this will be F by 2, this will be K by 2, things like this. So this is a magnitude scaling, the basic principle of magnitude scaling, so that the amplitude of the output at no point should exceed this plus minus 10 volt range. So this is the theme of the experiment that we should be covering in this semester. Previous to that, we have just given you theory of what should be the analog simulation of a given differential equation and what you will expect from as a response of the system that I will discuss in the next concluding part, where I will be showing you the actual video clips, okay, of this experimental setup. Today I'm not going to indulge into that because you have taken a lot of inputs, so I should give you some time to digest those inputs, and then we shall come back in the next class to digest this, and I shall provide you with all the required documents, okay, that scanned PDF version of these notes that you require to understand this scaling. The scaling I will not discuss. You first understand the basic analog simulation part. Then I'll give you some notes on the scaling, and I'll discuss in details the magnitude scaling in the next class. Okay? Everybody okay with that?
Yes, sir.
Okay. So what about the attendance? How should I take the attendance?
Sir, I don't think it is possible because, sir, some students are already outside of the meeting.
Outside, that is the point. So those who are outside, they are watching on YouTube.
So they will be watching on YouTube after I upload.
Nothing. Okay,
Yes, sir.
they will watch
Nothing.
only after I upload that.
Yes, sir.
Okay, let me just look at the participants. How many participants are there right now? 89.
Yes, sir. Now there are 89.
Now there are 89
It was
participants.
100.
When I started, it was 100. Okay, let's stop
Sir,
here.
based on previous labs, sir, everyone was present.
No, initially it was 100. So I will not give attendance since it's not mandatory to give attendance in these situations. I'll assume that all of you were there. What I can do in Gmeet, there is an option for chat where you can put your signature, raise your hand or something like that.
Yes, sir.
But in this case, I don't know whether there's any option or not. Gmeet I've taken based on Rajkumar Kanwar has raised his hand. I don't know whether this is
Yes, sir.
being
Here also
voted
we
or
can
not.
raise hand, sir.
or you can simply put your name and roll number in the chat window. Okay, all of you put your name and roll number